Okay, so topic of our today's discussion is isothermal processes, right? We have read about uh, heat transfer, latent heat, specific heat. Now today's lecture is thermodynamic processes. Okay, so we will define what are thermodynamic processes, what are quasi-static processes. We have done we have done this quasi-static part, what are quasi-static processes, but we will now discuss the characteristics of various thermodynamic processes, right? And we will be able to calculate heat transfer, work done, and internal energy for the isothermal, adiabatic, and uh, isobaric processes. Okay, so we have done these basics of isothermal thermodynamic processes. We have cleared these some of the terminologies that are going to be used, like your what are the different systems that we have done, what are quasi-static processes, non-quasi-static processes, what is work done by the system, and what is work done on the system, right? System surroundings we have already done. Your work done is the area under the your PV curve, pressure volume curve. We have already done this, right? And first law of thermodynamics, from which we get this equation: delta U is equal to Q minus W delta U, where delta U is the internal energy of the system, Q is the heat energy transferred between the system and the surrounding, and work done is work W is the work done by the system on to the surrounding. Negative here, negative here is representing that your internal energy will decrease. Your internal energy will decrease if the work is done by the system on the surrounding. Then the energy will be released by the system into the surrounding in the form of work, right? So that is why negative sign is there, that if the work is done by the system, then that work is going to be positive, but it will reduce the internal energy of the system, right? Because in doing the work, your system will lose its energy in the form of the work, uh, and that energy will be gained by the surrounding. Okay, so this is the equation that we got from the first law of thermodynamics. Then we studied that what are state functions, that only depends upon the initial and the final state, right? And does not depend upon the path. Okay, so we have uh, we have also done how to find out the work, what is going to be the formula for work for different processes, for isocoric, isobaric, and isothermal processes, what is going to be work done, right? So for isocoric, what is isocoric? Isocoric means where the volume is constant, right? So when volume is constant, that means uh, work done will be equal to zero, right? Because your what is your work done is basically equal to the area under the PV curve, right? So when volume remains constant, there is no area under the curve. So work in that case would be your zero. Okay, so in case of isocoric process, work done would be zero. In case of isobaric process, your PV curve is going to be straight line parallel to the x-axis, right? And area under the curve is going to simply the area of the rectangle formed under the curve, under the straight line, right? And in case of your uh, and in case of your isothermal process, what will happen? Uh, the curve will be PV curve will be a curvilinear path, and the area under the curve is uh, will be calculated using the integration, right? Integration of P into uh, change in volume, that is dV, integration from V initial to the V final, V1 to V2. Okay, so that's this is just the recap that we have done so far. Okay, so the internal energy U is a state function, right? So internal energy gain or loss only depends upon the initial and the final state, and not on the path. Okay, it only depends on uh, the present moment at which your system is, the state in which your system is at the present moment. Only on that your uh, internal energy depends. Okay, and what categorize the state of the system? Your variables. What are these variables? State variables. These are pressure, volume, and temperature. Right? Pressure, volume, and temperature, and also number of moles we are taking. Okay, so whereas your Q, that is the heat energy and work done, these are path dependent functions or path dependent properties, but your internal energy is only state dependent. It only depends upon the present state. Okay, so we have done this. So these are your basic thermodynamic processes. Adiabatic processes, what happen? There is no heat transfer between the system and the surrounding. So no heat transfer means delta Q is going to be zero. And how do we get the adiabatic process? By insulation or by very fast, or in case of very fast processes, we have adiabatic processes, right? Then isocoric means there is no change in volume. So because there is no change in volume, work done will be equal to zero. So delta W is going to be zero. So, so the all the energy in the form of heat that is being transferred between the system and the surrounding will result in the change in the internal energy of the system, right? Your internal energy of the system is dependent on your temperature. Okay, is dependent on the temperature. So whatever the heat is provided or exchanged between the system and the surrounding will result in all that will result in change in temperature, because there is no loss or gain of energy in the form of work, because your delta W is zero. So all the uh, all the uh, gain or loss of energy will be represented in the form of temperature change. Okay, in case of isobaric process, isobaric means your pressure is going to be constant. Pressure is going to be constant means that in isobaric process your curve will be, or PV curve will be a straight line parallel to x-axis, right? Similar to like this, your curve will be a straight line. So the work done is going to be area under the curve. So simply pressure into volume 2 minus volume 1. Volume 2 means volume at the final state, and volume 1 is volume at the initial state. Okay, so your work done is going to be simply pressure into change in volume, right? Whereas in isothermal processes, what happens, delta T is going to be zero, because isothermal means that temperature is going to be same, right? So constant temperature processes, uh, your delta T is going to be zero in these type of processes, right? So because there is no change in temperature, that means there is no change in internal energy, because as already been said, the uh, internal energy is reflected by, or change in internal energy is reflected by the change in the temperature of the system. Okay, so if there is no change in the temperature, that means there is no change in the internal energy. So delta U, or change in internal energy, is going to be zero. So your delta Q will be equal to delta W. So all that energy that is being provided will be in the form of work done. Okay, if work is done by the system on the surrounding, then all it is going to be the loss of energy uh, for the system in the form of heat, right? And if it is mm, if work is done by the if work is done by the surrounding of the system, then it is the gain of energy by the system in the form of heat. Okay, heat energy. So as we know, for isolated system, what is isolated system? In which there is no transfer of mass and energy between your system and the surrounding. So because there is no transfer of either mass, so your delta W is also zero, and there is no change in delta Q, or no transfer of heat between the system and surrounding. So your internal energy change will also be equal to zero. So initial your initial internal energy is going to be the final internal energy. Okay, for the isolated system. In case of your cyclic system, in case of your cyclic processes, what happens in cyclic process? Your initial state and final state is going to be the same, right? Your initial state and final state is going to be same. So your internal energy is going to be same. So there will be no change in internal energy. So delta nu is going to be zero. So all the uh, energy, all the heat and energy that is entering or exiting the system will be in the form of work done. Okay, so energy exchange between heat and work. In case of adiabatic processes, there will be no exchange of heat energy between the system and the surrounding. So delta Q will be equal to zero, right? There will be no transfer of energy in the form of heat between the system and the surrounding. So the equation that we got from first law of thermodynamics, that will become delta U is equal to minus W, right? So all so the change of change in internal energy of the system will depend upon the work done by the surrounding on the system, or work done by the system onto the surrounding. If work is done by the system on the surrounding, then internal energy is going to decrease. And if work is done on the system by the surrounding, then internal energy is going to increase. Okay, so in expansion means when work is done by the system, then your internal energy will decrease. And compression means compression of the system means that work is done by the surrounding on the system. So for that case, your internal energy will increase, right? And in case of your cyclic process, what happens? What is work done? Work done is how to find out the work done in PV diagram, as already been told. You but in you can see that the direction of the curve or the direction of the process will be different. Okay, so uh, you can see it is clockwise. The direction of your process, this these thermodynamic processes are clockwise, right? When it is coming from top to bottom, it is going in from the left to right direction, and when it is going from bottom to top, then it is going from right to left, right? So what will be the work done? What will be the area under the curve? Area under the curve. So what will be the total work done? What will be the total area? Because total area will be your total work done under the by total work done in the processes. So your total work done in this case will be uh, summation of area under the curve. Summation of area under the curve. Okay. But what happens that area for one process, area under the curve will be positive, and for other process that is in the opposite direction, area under the curve will be negative. So what happens? So the net area under the curve will be your area bounded by this circle, this closed curve. Okay. So the net area under the curve will be your area bounded by this closed curve. Okay. So work done will be equal to the area that is bounded by this closed curve. Let us see. An ideal gas is taken around the cycle shown in this PV diagram. PV means pressure volume diagram, from A to B and then to C and back to A to complete the cycle, right? Process B to C. Process B to C is isothermal, right? And we can see that process C to A is isobaric because pressure is remaining constant, and process from A to B is isochoric because volume remains constant. Okay, so we have all the three uh, isothermal processes in this diagram, that is isochoric, isothermal, and isobaric, right? For this complete cycle, a delta q, which of the following will be true out of these options a b c d e? Which of the option is true? First option says that q is greater than 0, w is greater than 0, and delta u is greater than 0. The second says, because we already know that for a cyclic process, delta u is going to be 0, because because your internal energy is the state property or state function. It does not depend upon the path taken, it only depends upon the initial and the final state, right? And here initial and final state is the same, and it is it is equal to the point A. Here it is represented by point A, so delta u is going to be 0. So this is our right option, right? And delta q is work is also greater than 0. Why work is greater than 0? Because it is in this direction. Volume is expanding, right? Volume is expanding. Okay, so volume is expanding, so that means work is done by the system. So what are the important formulas that we have uh, learned up till now that are frequently used and are going to be used further? First one is your delta U is equal to Q minus W. This we got from first law of thermodynamics, right? First law of thermodynamics state that energy neither is created nor destroyed but can be transformed from one form to another. So that is your first law. So from that law we got this, that internal energy, whatever the change is there in internal energy of a system, or in our case gas, it is going to be equal to the energy provided in the form of heat minus the work done, that is done by the system, right? And we know, we just did this in our previous class, that work, and revised in this class also, that work done is equal to area under the curve of a PV diagram, right? Your work is area under the curve under PV diagram. So it is, so that area under integration. Okay, so integration of P delta V, when your state of the gas changes from V1 volume V1 to V2. Okay, so work done, so work during a volume change, and this PV equal to nRT. This we got from ideal gas laws, from the combination of your Charles law, Boyle's law, and your Avogadro's law for ideal gas. When we combine that, we got the pressure V is your volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Okay. 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 We So for adiabatic processes, what happens in adiabatic processes, as we have discussed, no heat is gained or lost. In other words, there is no change in heat energy, right? No transfer of heat energy between your system and the surrounding. Delta Q is going to be your zero. So your equation uh, delta U, or delta U is equal to minus W. So we know that PV is constant for isothermal process, right? PV is constant for isothermal process. Why? Because PV equal to nRT from ideal gas laws. From ideal gas law, we get the equation PV equal to nRT. And for isothermal process, delta T is zero. So PV is constant. PV, but for adiabatic process, there is a slight change. It's similar to isothermal process. For adiabatic process, the only change is that we have V raised to the power gamma, and your gamma is Cp by Cv. And now what is your Cp, what is your Cv, we have done in our specific heat lecture, right? In our specific heat lecture, if you remember, what was Cp, what was C? C is your specific heat, and P means at constant pressure, and C is again your specific heat, and V in the subscript is implying that it is specific heat at constant volume. Okay, so your gamma is ratio of specific heat at constant temperature to the specific heat at constant volume, right? And for the monatomic gas, uh, gamma becomes 5 by 3. Okay, for monatomic gas, your gamma becomes 5 by 3. So for monatomic, the equation becomes PV5 by 3 is equal to constant. For diatomic gas, it becomes gamma becomes 7 by 3. Okay, so let us see with some examples. An ideal monoatomic gas is taken through a cycle diagram. If there are 0.0200 mole of this gas, what are the temperature and pressure at point C? Right? From the graph, we know that PC, pressure at C, kilopascal, right? Ideal gas law. P, we know, and R, okay, out the R. There is a relation. We have done this. We have done the isochoric process. We have done isobaric process. We have done isothermal process. Right now, heat capacity between your different heat capacity is this. Right, because we know. Uh, so consider an isobaric process. Isobaric process means delta P is going to be 0. Okay, delta P is going to be 0, and we know from the specific heat session, specific heat lecture, the heat uh, provided to a system is equal to uh, number of moles multiplied by specific heat multiplied by change in temperature. So all the energy provided by a all the energy provided to a system is resulting is, will result in change in temperature. Unless we are also taking unless it is an example of where heat of transformation is also occurring. Okay, is also there. Heat of transformation, you know that unless it is an example of when there is a change in the state of the matter, right? If it is turning from liquid to solid or solid to liquid, then some amount of the energy provided, that is qp, some of or q, some of the heat energy provided q, some of it will be uh, utilized in the form of heat of transformation, heat of fusion, or other transformation heats, right? But if there is no change in the state of the matter, then all the heat that is being provided to a system will be utilizing the change in temperature, right? So we know from that specific heat lecture session that your q, energy provided or heat energy, is equal to molar mass, that is number of moles, n, c, that is your specific heat, and delta t, delta is the change in volume. But here we are talking only 1 mole, so n equal to 1, and this is the case of isobaric process. So to represent that, it is Cp, okay, specific heat at for isobaric process, and delta T is your change in temperature, right? So your first law of thermodynamics become uh, change in uh, change in the heat energy, dqp, it is equal to Cp dt, okay, Cp dt, and it is equal to du by pdv, change in internal energy plus work, okay, plus work pdv. But we know from the isothermal processes, sorry, for mm, for your iso choric process, that uh, we derive from isocoric process that change in internal energy is equal to cv dt. Cv means specific heat at constant volume, right? So for isocoric process we get this expression du by cv dt, right? So in place of du you can place cv dt, and we know pdv is work done, and it is equal to nrt. Okay, nrdt nrdt. So this can be written as this, right? Here actually we are taking n equal to 1 for 1 mole of gas, so here n can be ignored. Okay, n can be ignored, it is equal to 1. So you calculate this, this becomes, this equation becomes like this. So the relationship between your cp and cv is equal to cp equal to cv plus r. You can ignore the n for one molecule of gas. Okay, for one molecule of gas cp is equal to cv by, sorry, cp equal to cv plus r. So in other words your r is equal to cp minus cv, right? Your r is equal to cp minus cv. Okay, so from here we can find out the value of r. Okay, so now let us come back to this question again. We have to find out the state variables, the temperature and pressure at point c. Temperature and pressure at point c, right? So from this diagram we can see that pressure at this point c is 98 kilopascal, and is given in the question, right? So p is known, n is known. We have to find out now what volume and temperature. Volume and temperature. So we know from the graph that volume is 2 liter. Okay, so you just we know volume, we know pressure, we know n, r. Because for monatomic gas, what is the value of cp by cv? Value of cp by cv is 5 by 3, right? Cp by cv is 5 by 3. From there we can calculate the value of r. So next part of the question is what is the change in internal energy of the gas as it is taken from point A to B. Okay, at it is taken from point A to B, what is the change in the internal energy? Because A to B is isocoric process. Isocoric means change in volume is zero, so there is no work done. So all the energy that is being transferred between the system and the surrounding, it is equivalent to, or it is equal to the change in internal energy, right? So your du, we know from the formula for du is uh, ncv dt, right? Ncv dt. So this 0.0200. cv, we know it is a monatomic gas, so cv becomes 3 by 2 r, 3 by 2 r, right? And delta t, we can find out delta v, sorry, t from this formula, right? So t at this point at b and t at a, we can find out using this formula. So substituting these value, we get the value of change in internal energy, that is minus 200 joule. Okay, so Yeah. Now the next per cycle work done is going to be here. So work done is going to be area bounded by the curve, area that is enclosed in the curve, right? And because it is counterclockwise, the work done is going to be negative. Work done is going to be negative. If it was clockwise, then work done would have been positive. It is in counterclockwise, so work done is going to be negative. Okay. So work done per cycle is the area between the curve on PV diagram, right? So what is the area between the curve? It is a triangle. We can find out the area. We know the area of a triangle, that is half uh, into base into height, right? Half base is your 2 minus 1, 1. Height is your 230 minus 98. Okay, 230 minus 98 divided by half. That is going to be your work done. Okay, so this is half multiplied by change in volume in is 66 joule of work done. Okay, and fourth part of the question is your what is the total change in internal energy of the gas in the one cycle. So we know that in cyclic process change in internal energy is always going to be zero, so it is zero. Okay, so that's it for today.